Let's talk about an application here of how we might see vectors arise in something a little less than just adding and subtracting or magnitudes. We've got an airplane that is heading due east. And that's what it says on its compass, right? Let's try that again. Here we go. So the plane is flying due east, but the tricky thing about planes is that they are flying and the air around them is moving. And so if they're moving relative to the air at a pure east direction, then it might also be pushed off course. The air might be moving in a different direction and bring the plane along with it. So this particular plane has a wind coming from the northwest, and that wind has a velocity of, or magnitude of speed, of 80 kilometers per hour. So what we can do here is make velocity vectors out of both of these quantities. They both have a magnitude and a direction, and we can obtain the net speed, or net velocity better, of this plane by looking at the sum of these two vectors. This is the net velocity. Okay, so I've drawn it, but that doesn't really answer the question of what that vector is yet. There we would like to go to components so that we can actually get the component representation. How much east, how much south is the makeup of this net velocity. All right, well fortunately the net velocity is just the sum of these two vectors here, and let's call that v plane. It's pretty clearly 600, 0 if we take our traditional x and y perspective, and that's east and north. The trickier one is the velocity of the air, but it's not too bad once we realize we're just dealing with Pythagoras here. There we go. If we have a velocity that's 80 this way, and it's at 45 degrees from the northwest, is assumed to be halfway between north and west, then what do we have? Well, we have it similar to another triangle that's root 2, 1, 1, or better yet, 1 over root 2, 1 over root 2, and 1. So these two sides here would be 80 over root 2 negative and 80 over root 2 positive here. So the velocity of the plane, sorry, of the air, the velocity of the air is going to be defined by the components x positive, we're moving to the right, so 80 over root 2, and the y value, or y component rather, would be negative because we're heading downwards, opposite of north, again with a magnitude of negative 80 root 2. So our net velocity vector is going to be 600 plus 80 over root 2, and 0 minus 80 over root 2, and there's not much we can do with that. I'll just leave it as that. That vector defines this quantity here that we sketched out on the diagram. Okay, let's add a little wrinkle here. You have an airplane now flying at an airspeed of 800 kilometers an hour and winds that are blowing from the south. So we know one of these vectors from the south at 50 kilometers, from, keyword here, that's our velocity of the air. In what direction should the plane head to end up going due east relative to the ground? Well, that's a little bit of a different beast here. Let's just move this out of the way. So here we're talking about a sum of vectors again. Oops, there we go. Except we know what we want our net velocity to be. Let's say this is our route. We've got 50 kilometers north. We know we want the final velocity to be due east. The only way for that to happen is for our plane to head this way in such a way, well, there's some angle here that's going to define the correct, we have to find the right angle so that we end up heading down and ending up due east after being pushed north by the air. And what do we know We don't know anything about the direction of the plane's vector, but we do know that its magnitude is going to be 800. So that's a different kind of scenario. We don't know what the net velocity is going to be, but we do know that this length is 800, this length is 50, and look at that. It's a triangle. So if we start building some triangular stuff here, there we go. We know the length of two of the sides, and we're trying to find something out about the angle, say this angle down here, because that's the same as the angle up here. We can use our classic Pythagorean identities, or trig identities here. What can we say? Opposite over hypotenuse. We know that sine of theta is going to equal 50 over 800. So theta is equal to the arc sine, or inverse sine, of 50 over 800. Make sure you check your calculator for degrees or degrees or radians. But let's do a shift sine of 50 over 800. And in radians, that's 0.0625. I'll be honest, we're not doing any calculus yet, so I would be tempted to put this in degrees. This is a navigation problem. Much more traditional to put that in degrees. So we multiply by 180 and divide by pi. We're talking about, again, these are both approximations because we're cutting things off, 3.58 degrees. What that tells us is that we need to aim the plane if we want to achieve this net eastward velocity here by the time we factor in the air pushing us north and our plane moving a bit south but mostly east. We need to needs to aim at 3.58 degrees south of east. All right, and that will result in a net direction of due east once the plane has made that decision. So that's another example of a vector type calculation, a little more in depth than the earlier ones, but still being based on sum of vectors, components of vectors, and how we might bring some of the earlier things that we had, like Pythagoras and geometric identities in general, into play.